Welcome back to part 2 of our video on U substitution. Example 4 says evaluate the following indefinite integrals. Part A says we have the indefinite integral of t to the fourth times the cubed root of 3 minus 5t to the fifth power dt. So in the previous examples, we saw a lot of scenarios where we had trigonometric functions, and here we have a slightly different kind of function. And a lot of times we want to try and make u the value that when we take the derivative of it, its derivative appears somewhere in the integrand. Now that's not always the case, but here I'm going to set u equal to 3 minus 5t to the fifth power. And note that when I take the derivative of this thing, I'm going to have something to the fourth power, and that already appears in my integrand. So I'm going to have du dt equals, I'm going to use the power rule, so negative 5 times 5t to the fourth power, and then I'm also going to solve for du. So negative 5 times 5 is negative 25 t to the fourth power times dt. And notice that t to the fourth times dt appears here and here. And I don't really have that negative 25, but I could divide both sides by negative 25, and that's going to give me negative 1 over 25 times du is equal to t to the fourth times dt. And that's going to be something we can substitute into our original integral. So this is equal to the indefinite integral of the cubed root of u. So I'm replacing that entire thing with u. And then t to the fourth times dt is getting replaced with negative 1 over 25 times du. Now, negative 1 over 25 is a constant. I can pull that outside of my integral. And I'm also going to rewrite the cube root of u so that it's in an exponent form. And that's the same thing as u to the power of 1/3. And then I still have my du inside of my integral. So at this stage, I can use the power rule. So I have negative 1 over 25 times u. I'm going to add 1 to my exponent. 1/3 plus 1 should give me 4/3. And then I'm dividing by my new power. And because we've integrated, I can introduce my constant of integration. So I want to clean this up a bit. I have negative 1 over 25. If I'm dividing by a fraction, I can multiply by the reciprocal. So that's going to be times 3/4. And then I have u to the 4/3 power, but I'm going to replace u with what we originally defined it to be, which was 3 minus 5t to the fifth power. And I'm going to keep my exponent there, and then I have plus c. And I'm going to move up here. I just want to multiply my fractions together. So negative 1 over 25 times 3/4 looks like it's going to give us negative 3 over 100, and then times 3 minus 5t to the fifth power raised to the 4/3 power plus c. And there is my final answer for part A. For part B, we want to take the indefinite integral of x squared times the square root of x minus 1 dx. Previously, I said that a lot of times we want to make our u value the thing that when we take the derivative of it, that derivative appears somewhere within the integral. This example is an exception to that general rule. So here you might say, well, what if we made u equal x squared? If I took the derivative of that, we'd get du dx equals 2x. And x kind of appears inside of the square root, but that's actually not really going to be helpful because du in this scenario would end up equaling 2x dx, and that wouldn't really get us anywhere that would be that helpful. So this is actually not the choice of u that's going to end up getting us anywhere. Instead, what I want to do is I want to set u to be the thing that's underneath the square root. So I'm going to set u equal to x minus 1. And if I took the derivative of both sides, I would get du dx is equal to the derivative of x is 1, and then the derivative of a constant is 0. And so we end up getting the relationship that du is equal to dx. Now, if I replace inside of my integral and I substitute, I would end up getting x squared times the square root of u, and then dx is just going to get replaced with du. And previously, we had said that we want everything to be in terms of u, and right now I still have an x squared, so prior to this example, that might have told us, hey, maybe we're doing something wrong and we should choose a new u value. That's actually not the case here. So what's going to end up happening is I want to take this relationship here. I want to take that u is equal to x minus 1. And because that is the way that we defined it to be, and that is an equation, as long as I do something to one side and I do it to the other side, they should remain equal. So if u equals x minus 1, if I were to add 1 to both sides, I would get the relationship that x is equal to u plus 1. Now, again, as long as I do it to one side and I do it to the other side, they should maintain equality. So from this stage, I'm going to square both sides. And if I do that, I end up getting the relationship that x squared is equal to u plus 1 squared. Now, what's going to happen is if I replace x squared in my integral at this point, I know that x squared is equal to the quantity u plus 1 squared. So I'm going to make that substitution here. And if I do that, we get the definite or the indefinite integral of u plus 1 squared times the square root of u du. Now, you might be asking, did that actually help us? Did that get us anywhere? And can we integrate this thing? The answer is yes. And u plus 1 squared is the same thing as u plus 1 times u plus 1. And if we multiply that out, we're going to eventually be able to distribute in the square root of u. So we saw in a previous example where we had something like a binomial, maybe it was something like 3x plus 1 to the 30th power. Multiplying that out would take a long time, but here we just have u plus 1 squared, and that's not too bad to multiply out. So if I did multiply that out, I would get u squared plus 2u plus 1, and then I still have that square root of u times du on the outside. Now, because on the outside I just have square root of u, I can distribute this in to each of these terms, and if it helps you multiply, remember the square root of u is the same thing as u to the 1/2 power. So at this stage we would get u, and then 2 plus 1/2 would be 5/2, and then we have plus 2 times u. 1 plus 1/2 should be 3/2. That would be my new power after I distribute. And then plus the square root of u times 1, I'm going to write that as u to the 1/2 power. And then I have du. So on each of these terms, I can use the power rule. If I increase the power by 1, I get u to the 7/2 power. And then if I divide it by 7/2, that's the same thing as multiplying by the reciprocal. So I have 2/7 as my coefficient, plus 2 times, if I increased my power by 1, I'd have u to the 5/2 power, and then I'm going to multiply by the reciprocal there. and plus u to the 3/2 power. Once again, my new power is 3/2, so if I were to divide by 3/2, that's the same thing as multiplying by the reciprocal. And then now that we've integrated, I can introduce my constant of integration. So our original value for u was x minus 1, and at this stage I can plug x minus 1 back in for all of my values of u. So here we have our final answer. In part C, we have the indefinite integral of x cubed times the square root of x squared plus 16 dx. Similar to part B, we're going to set u equal to the thing that's underneath the square root. So we end up getting that u is equal to x squared plus 16. And from here, if I were to take the derivative of both sides, I'd end up getting du dx is equal to 2x. Now, if I solve for du, I get du equals 2x dx. And now I'm going to divide both sides by 2. If I do that, I get 1/2 du is equal to x dx. Now, outside of my square root, I have an x dx, and I'm going to get it by doing this. So instead of writing x cubed, I'm going to rewrite x cubed as x squared times x. And then I have the square root of x squared plus 16 dx. And if I rearrange this a little bit, this is equal to the indefinite integral of x squared times the square root of x squared plus 16. And I'm just moving the x to the end. So I have x times dx. And the reason that I'm doing that is here I have x times dx is equal to 1/2 du. So I have the indefinite integral of x squared, and then underneath my square root, I could rewrite that as the square root of u, and then x dx I'm going to replace with 1/2 du. So we still end up with the issue of having two different variables, and so the way that we're going to fix this is kind of similar to the last example. I know that u is equal to x squared plus 16, and if I solve this equation for x squared, I end up getting the relationship that x squared is equal to u minus 16. So in my indefinite integral now, I could rewrite this as, I'm also going to factor out the 1/2, and then x squared I'm going to replace with u minus 16. And then I have times the square root of u, which I'll rewrite as u to the 1/2 power du. So just like last time now, I'm going to take this u to the 1/2 and I'm going to distribute it into my parentheses. And if we do that, we get 1/2 times the integral of u to the 1/2 plus 1 is 3/2, and then minus 16 u to the 1/2 power du. And on each of these terms, we can use the power rule. So if I increase the power on u to the 3/2 by 1, that's going to give me u to the 5/2 power, because 3/2 plus 1 is 5/2. And if I divide by 5/2, that's the same thing as multiplying by the reciprocal of 2/5, minus 16 times, I have u, and if I increase the power by 1, that would give me 3/2. And I'm going to multiply by the reciprocal, that's going to give me that. And I have my constant of integration. So from here, I can distribute in the 1/2 inside of my brackets. So that's going to be 1/5. And then I can also replace my u and substitute back in x squared plus 16. And then if I distribute 1/2 into the next term, so I distributed it here already, and then I'm going to multiply it there, what's going to happen is the 2 in the numerator and the 2 in the denominator are going to cancel out. So I should be left with minus 16 over 3 times x squared plus 16 to the 3/2 power plus our constant of integration. And this represents our final answer for part C.